Guys, this is Mr. Billemeyer. We're here for another video tutorial. Today we're going to be learning lesson 10.5, reading scientific notation. So let me first explain what scientific notation is. Scientific notation is just another way to write a number, but usually we use it when we're writing either really, really small numbers. For example, something like this that I'm about to put on your screen, 0.000000314. All right, so that's a really, really small number. Or we could use scientific notation when we're trying to write a number that's really, really big. For example, 926, 000, 000, 000. I think that's 926 billion. But the reason that we write these numbers in what we call scientific notation is because it's easier to do math operations when they're written in scientific notation than the way that they're written on the screen right now. For example, let's say you had to multiply these two numbers together and get an answer. Well, that's a whole lot of numbers to multiply together and carry numbers and add zeros as placeholders as you're going along. It becomes really, really difficult and really, really easy to make a mistake. So later in the next couple of lessons, when we do operations with these numbers in scientific notation, you understand why it's, why they're used, because it's easier to do the math. And then you might also wonder, like, where are these numbers? Like, who's actually using this stuff? Let me get rid of this here. Well, as the name kind of indicates, it says reading scientific notation. So the word scientific there kind of gives you a hint as to where these numbers might be used. Most of the time, they're used in like the world of science. For example, if you were a chemist, you might be dealing with a number of atoms inside a particular substance, and that number would be super, super big. And instead of writing it out with all these zeros like I had done with the 960 billion, it's easier to write it in scientific notation, because then it's easier to work with. Or maybe you're a biologist and you're talking about how small or how thin a cell wall is. That's going to be a really, really small number. So it's easier for them to use it in scientific notation than to use the actual number with the decimal point and all those zeros. All right, so that's the why as to why these numbers exist. All right, so let's get into what these numbers are, and then identifying them and recognizing them. So a scientific number. A scientific notation number is a number that's made up of two factors. So we're taking a regular number. Let's say, for example, we had the number 50, right? We could rewrite that number 50 as factors. We could break it up into two factors, 5 times 10, okay? Oops. And that's all scientific notation is doing. It's taking a really, really big or really, really small number and breaking it up into two factors. All right. And that's what we're looking at down here with this number, 8.3 times 10 to the negative 7. All right. So we like to call the 8.3, this number here, the 8.3, we like to call that the first factor. All right. And then the second part of this, the second factor, we just call the base 10 factor. Wow, sorry, my writing's a little tough here. All right, the base 10 factor. So the first factor, if you look at this box right here, there's something about the first factor that always has to be, it has to be a number that's between, it could be equal to 1, but it has to be basically between 1 and 10. It's allowed to be equal to 1. It's not allowed to be equal to 10, okay? And it always has to be that way. So numbers like 0.76 don't work because that number's less than 1. So it doesn't fit, between 1 and 10, so we can't use it. So this one's no good. And neither is a number like 247 because that's bigger than 10. and it doesn't fit between 1 and 10, so we can't use that number as well. All right, let me erase some of this stuff here. All right, so again, just to emphasize again that this number has to be between 1 and 10. It's allowed to equal 1. It's not allowed to equal 10. Another way to look at it is if you look at this, you can see that there's only one number, the number 8. There's only one number that's not 0. It can't be 0, but there's one number to the left of the decimal point. So as long as there's only one number to the left of the decimal point and that number is not a 0, then that first factor is okay. The second part is this base 10 part. All right. It's always going to be the number 10. That's our base. And then that number 10 is going to have some exponent. It could either have a positive or a negative exponent. And in some situations, that exponent might be a 0. And we'll get into those special cases at some point. Okay. All right. So let's take a look at identifying some numbers written in scientific notation. So they want us to tell whether the number is written in scientific notation and then explain. So when we look at example A, what I want to look for, the thing that's really key is I want to look at the first factor. Is that number between 1 and 10? And 5.9 is between 1 and 10. Another way to look at it is there only one number to the left of the decimal point, and is that number not 0? And yes, the 5 is not a 0, and it's the only number to the left of the decimal point. So then that's okay. And then we look at the base, and if it's multiplied by a base 10 with some exponent, then both of the conditions are true. So then we can say that yes, this is written in scientific notation, and it's because 5.9 is between 1 and 10. Remember, it's allowed to be 1, it's not allowed to be 10. But if you write down it's between 1 and 10, we're going to understand as math teachers what you mean by that, and we'll be okay with that. All right, in example B, we're going to take a look at our first factor. Our first factor is 0.9. This is not between 1 and 10. It's less than 1. So therefore, automatically, this is a no. This is not in scientific notation because the first factor is not between 1 and 10. So then we would say it's not because 0.9 is less than 1. Okay? It's as simple as that as far as identifying whether something's in scientific notation. Look at the first factor. Is it between 1 and 10? If so, make sure you're multiplying by a base 10 with an exponent, and then you can say yes or no. All right. Okay, let's move on. Okay, so we're going to write some numbers in what we call standard form. So let's talk about that. We're going to be given, like if you look down at example 2, we're going to be given a number that's written in scientific notation. This 3.22 times 10 to the negative 4th power, right? And they're going to ask us to write it in standard form. Well, we have to understand what standard form is. And it's real simple. Standard form to us just means the way we're used to seeing a number, all right? Just the regular way of writing a number. So that's all I'm going to write up here. It's just the regular way. Sorry, my writing is terrible here with this stylus, but we're doing the best we can. So it's the regular way to write a number. Okay? So when you see a number like 172, that's in standard form. Or if you see a number like 0.742, also in standard form. It's just the way that we're used to seeing numbers, okay? Now, there's a couple of points here, right, about moving the decimal point. And so when we get into example 2, we'll kind of explain what that means. But when we move the decimal point a certain direction, right, it's telling us that the base 10 exponent is going to be a certain sign. So if we have to move the decimal point to the left, that means the exponent's going to be negative when we put it with the base 10. And if we're moving our decimal point to the right, it means our exponent's going to be positive when we put it to the base 10. And when we look at example 2 and further examples, you should understand what I mean. Okay, so let's go to example A. So we want to write 3.22 times 10 to the negative fourth in standard form. So the first thing we're going to do, step 1, is we're going to take that 3.22 and we're going to write it down. There's a decimal point there. Okay. And, excuse me, what we're going to do here is we're going to look at the base 10 because the base 10 exponent is going to tell us to move the decimal point a certain number of places. So this base 10 has an exponent of negative 4. So that means we're going to move the exponent 4 place values, all right? Because each one of those numbers is a place value that we're going to move it, a factor of 10, right? But since it's negative, it's telling us that we should be moving that that decimal point to the left 4 places. So I'm going to take this decimal point and I'm physically going to move it 1, 2, 3, 4, and I'm going to rewrite it down here, right? I moved it 4 places to the left, and that matches the negative 4, right? Not 4 places past the 3. You'll notice that the first place value that I moved it was just the first one gets it past the 3, and then there were 3 more, okay? So step number 1 would be to move the decimal 4 places in the direction you need to move it, and in this case, it's to the left. Step number 2 would then to be fill in all those empty little spaces with zeros. So 1 here, 1 there, and 1 there, and I filled them in. And now I'm going to rewrite this number so that it looks neat, right? So I'm going to put the decimal point, right? And I have 3 zeros, and the 3, the 2, and the 2 that were originally in my scientific notation. And the last thing that I want to do here is in mathematics, we don't like to have decimals that don't have something in front of them. So we're going to add 1 extra 0 out front so that we know that this is smaller than 0 when we're done. All right. I mean, smaller than 1, not smaller than 0. It's going to be less than 1. So this 0 that goes out front here tells us that this number is less than 1. All right. And there's a little key thing for us to realize here. If we have a negative exponent is always going to lead to a number that's less than 1. So the number has to be less than 1. Another way to think about that is if you have a negative exponent, numbers that, like scientific numbers that have negative exponents, always means that you're dealing with a really small number, okay? It's going to be a really small number. So that's how I like to explain it. If you see a negative exponent, you should have a small number, which means it should be a decimal, okay, with some zeros in there. Usually. Doesn't have to have zeros, but it's at least going to have that decimal with a 0 to the left. It's always going to be less than 1. All right. Let's take a look at example B. So we're going to write 7.9 times 10 to the 5th in standard form. So we want to make it look like a regular number. So we're going to start by taking the first factor and rewriting it. Okay. And now the base 10 exponent is a 5, and it's positive. So that tells me I need to move my decimal point to the right. So I'm going to move it to the right 1, 2, 3, 4, 5, and move my decimal point down there. And then I'm going to put zeros in for all of the empty spaces. Okay. And then, of course, again, I'm going to rewrite this number so that it's neat and we don't have all these little lines mixed in with our number. So I'm going to rewrite this number. Remember, this exponent up here is no longer there anymore. We moved it all the way to the right. So it's just going to be 7. Oops, sorry about that. 7, 9, 0, 0, 0, 0. Now, if you put this decimal point down here, all right, when we look at that number, we don't ever write numbers that don't have anything to the right of the decimal point. We don't ever leave the decimal point there. So I'm just going to get rid of that decimal point. It doesn't need to be there. All right. So we're just going to leave it out. All right. You only need the decimal point if you have non-zero numbers to the left and the right of it. Okay. Or if the number is going to be smaller than 1. But if the number is bigger than 1, we don't need the decimal point if there aren't any numbers to the right of it. So we're going to just get rid of it. Now, the last thing that you might want to do is you might want to put commas in your number so that you can then identify what kind of number you have. So every 3 digits starting from the right, we put a comma. So there's a comma there. So this answer is 790,000. Okay. All right. All right, we're going to move to the next page. So let me get there. All right, so you see there's some on your own problems here. So what we would like you to do is pause the video right now, take out a piece of paper and a pencil, and then work on these problems on your own. So there's 4 of them here. So go ahead and pause the video, work these out, and then start the video again, and then I'll go through the solutions. Okay, hopefully you guys have taken care of this and you're ready to check your answers. So number 1 is 12 times 10 to the 4th written in scientific notation. So what I do here is I take a look at the first factor, and that first factor has to be between 1 and 10, and 12 is not between 1 and 10. So this is a no. And the reason is because 12 is not between 1 and 10. 12 is greater than 10. Okay. So it can't be scientific notation. And then down below, number 2, we have 6 times 10 to the 7th. They want us to write that in standard form. Now, this one might have been a little tricky for you since it didn't have a decimal point in the number, and neither of our examples was like this. So we'll go through this now. First thing I'm going to do is I'm going to write this 6. Now, there's no decimal point there, so we always assume that the decimal point would be to the right of this number. So there's a decimal point right here. Not a dash, a decimal point. So I'll try to make it better. All right. So now the exponent with our base 10 is a positive 7, which means we're moving the decimal point 7 places to the right. So 1, 2, 3, 4, 5, 6, and 7. And our new decimal point would be down here. And we would fill in all these empty spaces with zeros. It's a lot of zeros there. And then we would rewrite the number with all those zeros, and we won't need the decimal point because it's all the way to the right and there's no other numbers to the right of it. So we're just going to rewrite this as 6. And it looks like I have 1, 2, 3, 4, 5, 6, 7 zeros. 1, 2, 3, 4, 5, 6, 7. And then let's put some commas in every 3 digits. So a comma there and a comma there. And then we're done. For number 3, we're going to start with 9.9. Now, I noticed that the base 10 is negative, so that means I'm going to move my decimal to the left. So I'm going to give myself some room to do that. So I'm going to write my 9.9 over here. And the negative 5 is telling me to move to the left 1, 2, 3, 4, 5 places. And here's where my new decimal point is going to be. And I'm going to fill in all those empty spaces with zeros. And then I'm going to rewrite my number, decimal point. I have 1, 2, 3, 4 zeros. And the 9s that I had in my original number. Sorry, that's a 9. And we're going to place a 0 out in front because we don't like a decimal point with nothing in front of it. Okay, so there we go, 0.000099. And then lastly, we're going to start with 1.285. I noticed that my decimal, or my exponent for base 10 is a positive 4. So I'm going to be moving my decimal to the right. So I'm going to give myself some room to do that. And I'm going to take my decimal and I'm going to move it 1, 2, 3, 4 to the right. Decimal point's now down here. Add a 0 in for the empty space and then rewrite my number. 1 point. Sorry, no point there. my bad. 12850. All right, don't make the mistake that I just made, which I've seen a bunch of times. I see somebody put the original decimal point into the new number and they end up having the wrong answer. So make sure you only have the decimal point. Once we move the decimal point, it's no longer there. All right, so please make sure that you don't make that mistake that I just did.